We've seen how to learn these values, Q's and V's, using Q value iteration or Q policy iteration or policy iteration. And we've seen that if these state transitions and your rewards are exactly observable, you can actually converge to the optimal policy. So that's actually the first set of algorithms. There's some limitations here. First of all, you actually have to initialize a value of your Q's or your V's. You have to initialize these values for all states. And if you're working with Q's, you have to initialize it for all states and actions. So this essentially only works if you have small discrete state and action spaces. You can't really do this method if your states are images, because you can't possibly enumerate all possible images. And likewise, the updated equations require fully observable MDP and exactly known transitions, which is usually a very strict assumption in the real world. So our next set of algorithms would actually extend these formulations. Instead of solving them exactly, we're actually going to try to solve them using function approximation. And we'll see how that helps us to solve MDPs with more uncertainty involving the transitions. So you recall, let's just look at Q value iteration. What Q value iteration did was that we first derived this Bellman equation, right? At optimality, we knew that your Q stars should obey this equation. And what we can do is, we derive this iterative method that initialize these Q stars to be some random initialization. And we're going to iterate Q star of K and compute Q star of K plus 1 on the left-hand side. So this equation is problematic because you actually have to do this exact summation over your states, your next states S prime, with your exact transition probabilities. So if you don't know these transitions, you can't compute this. So what can we do? So we can rewrite this Q value iteration as, instead of an exact summation over your next possible states weighted by your transitions, I can rewrite it as an expectation over next possible states given by the transitions. And if I rewrite it by an expectation, what I can do is that instead of computing the expectation exactly, I can approximate it just using Monte Carlo sampling. So what that would involve is, for any state action pair that you see, you're going to interact, you're going to start with a state, take an action, and the environment is going to return to you your next state, right? So you can collect a bunch of these next state action, next state pairs by just simulating and exploring in the environment. And that allows you to get a bunch of these triplets, S, A, S prime, so that you can actually approximate this expectation using samples. So just in the case of one sample, assuming you're just using like an estimate of using one sample, what you would do is that, again, in these iterative methods, you want the left-hand side to be equal to the right-hand side, right? So treat the right-hand side as your target, your reward plus your gamma discounted value functions for the next states. Treat the right-hand side as your target, and any error between the right-hand side and the left-hand side, I'm going to treat that as my error. So at optimality, the left-hand side should be equal to the right-hand side. So any excess difference between the left-hand side and right-hand side, I will treat that as my error. And you'll basically want to minimize this error towards 0. So how would you do that? Basically just compute the difference, treat it with your learning rate, and set Q of K plus 1 as your previous estimate plus alpha multiplied by this error. And this will slowly kind of tune your Q of K in the direction of this error, whether this was an overestimate or underestimate weighted by the learning rate, so that your Q of Ks and your Q of K plus 1 will follow this inequality. So here's actually a very easy extension to a new algorithm. So I'm going to start by initializing for all my states and actions my Q0, my initial estimate on my Qs. I'm going to start an initial state. I'm going to sample an action A and get a next state S prime. So if S prime is a terminal state, I'm going to treat my target as just a particular reward. So again, this is my optimality equation, right? So if S prime is already a terminal state, you're no longer interacting with the environment, then this all goes to 0, and your target is just your reward. Otherwise, your target is this term on the right-hand side. So the immediate reward that you observe plus your discounted values, expected discounted values in the future. And we know that our optimality, your left-hand side should be equal to the right-hand side. So any excess error would be the difference between your right and left-hand sides. I'm going to treat that as an error, which I will then try to optimize for by this gradient-based method. It's not really a gradient-based method because we're not really taking gradients. So it's more of like a zero-order optimization method. So by choosing a specific learning rate and optimizing Q of k to be closer to Q of k plus 1, you're actually trying to minimize this error so that you're getting better estimates of Q star that respect this optimality condition. So this step here is actually really important. We've seen, we've seen that you're not actually able to compute this expectation exactly because you don't know these transitions, right? So you want to be able to sample a bunch of SA and S prime from the environment so that you can actually, can kind of approximate these expectations using samples. So how would you actually sample an action A? You could choose random actions all the time. You could choose actions that maximize your current value of your estimates, so basically your current policy, greedily. Or you could choose something that's epsilon greedy. What that means is that you would choose a random action with probability epsilon, and otherwise you would choose the action that best maximizes the current value of your action value functions. So this is actually a very important concept in reinforcement learning, that of doing epsilon greedy sampling of your actions. Why do you want to do that? So we know that initially your QSA, which you've just initialized, is going to be very bad. So following QSA would actually mean that you're taking a lot of suboptimal actions. And therefore, your bad initial estimates would drive your policy into very suboptimal regions. And you will never see subsequent states that you care about that give you good reward. So what is usually done in practice is that with probability 1 minus epsilon, you would choose the best action according to your current estimate of your action value functions. But otherwise, with probability epsilon, you would choose a random action. And you want to set this epsilon to be really high, maybe even 1 at the start. You're treating these random actions, so you're actually exploring sufficiently in the environment. And as your policy is being learned and keeping track of the good actions with good rewards, you would want to take these good actions under your policy rather than taking random actions in the future. So you're trying to gradually decrease your epsilon as your policy is being learned using this algorithm. So the best possible choice here is to do something epsilon greedy, starting with random action with probability epsilon, with epsilon really high at the start, and slowly decaying epsilon such that you're taking actions based on your current estimates of your action values. So this is essentially our next algorithm. This is a very simple extension of our policy and value iterative methods, so that instead of computing the expectations exactly, you're just taking a bunch of samples, so that you're taking a bunch of samples and computing these expectations approximately. And this is a slide from Berkeley's class. And the amazing result is that this actually converges to your optimal policy, even if you're acting suboptimally. So you're acting suboptimally because all these state and actions that you're sampling from the environment, they're based on your current estimate of your action value functions. And at the start, these are going to be very bad, right? You're only going to, with random chance, get into high good states with high rewards. So a lot of these states that you're going to be learning and training these Q values are going to be bad states with very low rewards. But still, you can actually show that this converges to your optimal policy, even if you're acting suboptimally based on the current estimate of your policy. And this is called off-policy learning. There's been a bunch of research in this. But again, these methods are quite hard to tune because you have to explore enough, you have to make the learning rate small enough, but not decrease it too quickly. And this exploration problem is exactly why we need to be careful of how to do epsilon greedy. We have to make sure that we are sampling actions randomly so that you're exploring the environment enough before you actually start trying to take actions under your current value of the policy. So this exploration is always a very big research question in reinforcement learning. How do you encourage your agents to explore the environment enough and find regions of high reward better than just randomly sampling actions? So this algorithm is called tabular Q-learning, or just Q-learning for short, but sometimes referred to as tabular Q-learning. So why is this called tabular? So it's called tabular because you're initializing for all states and actions your QSAs. So what that means is that you want to keep a table that has number of size of S rows and size of A columns. So you have this table where each entry is QSA for a particular state and action. And this is still not ideal because it can only work for small and discrete state and action spaces. So again, if your states is images or your actions are continuous, then you can't really do this. And again, you can't really generalize to states that you've not seen before. So you will only be, everything here, you'll only be learning these estimates, your Q estimates for S and A for states and actions pairs that you've seen. So you're not going to be able to generalize to new states. So how can we solve that? So the next algorithm, we're going to see that in the next algorithm, but before that, let's just summarize this tabular Q-learning real quick. We started with MDPs with unknown transitions. You can't really compute this exactly. We're going to still use these Bellman optimality equations as given by this. So the optimality, these are equal as derived. And instead of computing this expectation exactly, you're going to replace this true expectation with estimates. So what that means is that you're going to sample a bunch of S prime just by exploring and simulating your environment. You have to make sure it's epsilon greedy so that you explore enough and get states of high reward. You know that this is your optimality equation. At convergence, the left-hand side should be equal to the right-hand side. So any divergence between the left and right-hand side, I'm going to treat it as my error. So this part will be your error. And you're going to optimize for this error using zero-order gradient methods by defining a learning rate and updating your Q of Ks to be closer to your Q of K plus 1s as weighted by the amount of error that you're currently making. So that is essentially tabular Q-learning. Again, the issue is that it's tabular. It requires small and discrete state and actions, and you can't generalize to unseen states. So how can we solve that? So now we're going to our last algorithm for the day, and that is extending tabular Q-learning to deep Q-learning. So using these high-level, using these recent deep neural networks with function approximation and combining them with Q-learning. So the goal here is to use these neural networks to be able to extract informative features from these high-dimensional input states, such as these images, so that you can actually do Q-learning instead of having to iterate over all states and actions. So the idea here is very simple. Instead of defining a QSA as a table over all states and actions, I'm going to amortize it by just learning a set of weights W. So this set of weights W would take in a state and take in an action, run it through some parameters W, and output QSA given W. The other alternative is that just take in a state, run it through some parameters W, and output your QSAs for all actions, across all your action spaces. So essentially the goal here is, so this works very well. And this is a very simple extension because instead of storing this table of all your QSA values, I'm just going to try to learn this table directly by taking in states and actions and learning just one set of parameters W. And this works for high-dimensional continuous states. If you have an image here, you can appropriately choose your convolutional networks. If you have states being both images and text, you can use your convolutional networks and your transformers. And you can also generalize to new states. So we know that deep networks, these function approximators, they can generalize because if you give it one particular image and you give it a very similar image with similar semantic concepts, you'll most likely make similar consistent predictions. So likewise, using these function approximators also allows you to generate to new states that are similar, but not exactly the same as the ones that we've seen before. So how would you train such a model? Again, you don't have these labels. These can't really train using supervised learning. So how would you train it? Training it actually involves many of the similar ideas as Q-learning. So again, you have these Bellman optimality equations, right? That relate your optimal Q star with your optimal Q star and next states and next actions. We know that we want to learn these Q stars such that this holds exactly. So you're going to start with a particular set of weights. where these left and right side are going to be different because you're going to start with a random set of weights. You're not going to obtain this optimality condition. So again, whatever the difference is, I'm going to compute the difference. I'm going to treat that as a loss function. So in other words, treating the right-hand side as a target, computing that, and basically the left-hand side should match the right-hand side. And any difference, any squared difference or absolute difference, I'm going to treat that as my error and try to minimize that to 0. And if I do minimize it to 0, then these Q values should respect these optimality conditions. So we've seen that a method similar to this, if I use like a table lookup for your Q stars S prime and A prime, it converges exactly. That was your tabular Q learning method. But if you kind of replace it, if you go from a table lookup method to one of these methods that you learn these parameters W using your neural networks, it's actually much harder to train. So obviously you no longer have these convergence guarantees. And sometimes it might also diverge. And there's two main issues, two main details that we have to fix before we can actually get this function approximation methods to work. So one thing is that problem of correlations between samples. So let me draw an analogy. So when you want to train for image classification, and you have maybe different categories, you have your cats, your dogs, your humans, your tables, and so on. Every batch which you want to put into your neural network to train these image classifiers, they should contain an equal sample of these different categories, right? That basically means that the samples I put into my neural network should be as uncorrelated as possible, so you can best learn a classifier across different uncorrelated samples that you want to classify in between. You want to classify with respect to. And if you just do this naively by neural networks, so you're going to get a lot of correlations between samples. So why is that? So you're going to start with S, you're going to observe a next state, you're going to take action A and observe a next state. So that is one particular data point, your S, A, S prime that you're going to give to your model. And then you're going to start from this S prime, treat that as a next state, take another action and go into another state. I'm going to treat that as a next data point. I'm going to take that next action, take another next state, get another next action and put that into the model. So all of this sequence of S, A, S prime, your data points that you're giving it into the model, these are all extremely correlated because they are from the same trajectory. They're from subsequent states from the same trajectory, right? So they're almost exactly very highly correlated. So that's one reason why it might not work. Another reason why it might not work is that problem of non-stationary targets. So again, if you look at image classification, for a particular set of images, your labels are always the same, right? You've labeled your data set once, you never change the labels, and you just iterate through the data set multiple times to learn a good classifier. But what's happening here is that we've kind of treated our right and left-hand side as the target, the difference between the right and left-hand side as a target. But every time I update my parameters W using gradient descent, the same targets for the same states and actions are going to change, right? So if I just keep my state and action constant, my initial value of W is going to give some value of your Qs. If I update W using gradient descent, I'm going to get another value of your Qs. I'm going to get different values of my Qs each time as my weights are getting trained. So that essentially has the analogy of doing image classification, but your labels are changing all the time. And right now I'm labeling this as a cat, and for the same image, a few epochs later, I'm going to label it as a dog. So this is a problem of non-stationary targets. And again, that makes it very difficult to train these models. So empirically, there have been two solutions proposed. Firstly, to remove correlations, a very easy method is to just first start by collecting a bunch of samples. So one trajectory would take S1, A1, observe next reward, the next state, and then from the next state, take next actions, next reward, next states. I'm going to collect all these trajectories before you even start training. And then I'm going to put it into a data set. I'm going to shuffle it, and I'm going to sample a random mini batch of transitions. So by shuffling and sampling a random mini batch, then I'm going to decrease my correlations between subsequent data points that I give into the model. Again, when you're collecting this data set of experiences, which we call the experience replay, it's important to explore and use epsilon greedy methods. So at the start, maybe before you even start training the model, you will just collect a bunch of random states and actions And your hope is that, for some of these, you're going to have high rewards. And those will be informative in training the model. And then as you slowly train your model and you get better estimates and you get better policies, then you can decrease the value of your epsilon and rely more on the current value of the policy as given by the model. So more of these state action reward pairs should have high rewards. And you're going to constantly kind of update your experience replay buffer. So that's the first thing. That's to remove the effect of correlations. The second thing, which was that of non-stationary targets. So the idea here is that you're going to you're going to fix some Q targets. So whenever I sample a random mini batch, I'm going to compute one of these targets. So in this case, the right-hand side, using W minus. So W minus is a set of old parameters that I have fixed maybe a few hundred, 1,000 epochs ago. So I'm going to fix these. This set of W minus parameters is not trained. These are that give my targets. And I'm just going to train my parameters W that give the outputs to my model. So keeping the targets fixed with a fixed set of old old network parameters. And I'm only going to update the network parameters that gives you the output of your model. So this, to some extent, can help you reduce your non-stationary problem because now your targets are fixed. They're no longer changing. And after maybe 1,000 iterations, then I'm going to replace my W minus with W. So I'm only going to do it every 1,000 iterations. So this is the method of using fixed Q targets to better reduce the problem of your non-stationary targets. And this is actually a very, very useful algorithm, I think. This was one of the main algorithms that contributed to the success of deep reinforcement learning recently. And because this method, by combining your Q-learning methods with your function approximators, your deep neural networks are able to do many tasks very well. So for Atari, for example, they've come up with these convolutional networks that take in these images. So these are all these games that are really high-dimensional images that you can't possibly train using tabular methods. But by using convolutional networks, you can actually learn very informative features that allows you to learn quickly and generalize to next states, to different new states. So one thing to take note of is in their method, instead of just giving it a single frame, a single frame for S, they actually stack raw pixels from the previous 4 frames together. And what that does is that it actually encourages the Markov property. You can think about why that's important. So just to give some intuition. So let's say you have these these games like Breakout, where you have to not only keep track of the current state of the ball, but you also have to keep track of the trajectory of the ball. So whether it's moving up or moving down. So like a single state of the ball isn't enough. So the designer method that actually respects this Markov property, you can actually take the previous 4 states. I mean, ideally you would take all previous states, which up until the Markov property holds. But I guess in practice, you can't take a bunch more states. 4 is like a reasonable number. So if you take 4 states, you can actually track the position of the ball over the past 4 frames. And that actually allows you to predict the next state and next action accurately without relying on information from frames even before that. On the other hand, if you just have a single state, you're actually not able to predict the next state or next action because it does not respect the Markov property. So if you have a single state, you actually need to depend on the previous state before that just to even know where the trajectory of the ball is going up or down, right? So just keeping one state doesn't actually respect the Markov property. So this general method, these deep Q networks do really well. These are all the Atari games. Some of which, if you look on the left-hand side, these are like 3,000% better than human performance. And these are usually the games that requires reaction speed. So, obviously, training these AI, they'll have excellent, almost perfect reaction speed. They also have a short-term reward. So if you look at this game, you're always observing reward whenever, within like a few frames, you're observing reward from breaking out these tiles. And you don't need that much exploration. So these are perfect settings where deep RL works much better because they're very good at exploiting short-term reward, and it's very difficult for them to explore, and they definitely have much better reaction speed as compared to humans. So these settings, deep RL is much better than humans. On the other hand, you have these games like Montezuma's Revenge, where performance is still at 0%. This was in 2016. Obviously, nowadays there's better methods, but at least these vanilla DQNs, performance is still at 0%. And why is that? Because these types of games have super long-term reward, requires a lot of exploration, and also requires knowledge of these complex dynamics. So these games actually involve things like, picking up a key and opening a door and going up a ladder. So humans know that, you want to pick up a key to open a door. But for AI that's trained from scratch, you don't know that. They don't know that. So these are much bigger challenges for DeepRL. But recently, I think 2019, they've also been able to come up with much better methods for playing these games. So now you see, picking up these keys and waiting for these barriers to open and picking up these jewels. And obviously, these are not just vanilla DeepQ networks. A lot of these methods are based on maximizing curiosity. So curiosity can be seen as, giving the model external rewards instead of just relying on the super sparse rewards in the environment, right? So curiosity is one method of just asking the agent, how well can I predict my environment? So if I cannot predict my environment well because I've never seen it before, or because it's stochastic, or because I don't know the dynamics of the environment, I should perhaps explore that region more. So curiosity and all these other auxiliary reward methods have emerged as strong methods to kind of supplement the rewards so that you can better train your models. Cool. So just to summarize, we've gone through a lot today. So what we started with was these fully known Markov decision processes with perfect states, transitions, and rewards. If you knew all of these, you could define this set of equations, both Bellman optimality equations. Those are equality equations involving your Q stars and V stars, which, given a state or action, tells you the expected long-term reward under the optimal policy. And likewise, we also derive these Bellman expectation equations, which under a state or a state action, compute your long-term rewards under a particular policy, pi. And we showed how to solve these, either through these value iterative or policy iterative methods. And if you know all these MVPs exactly, they converge. But the limitation is that it only works for small and discrete state interactions and requires known transitions. And we also saw an extension of how we went from perfectly knowing these transitions to actually sampling states and approximating these transitions, approximating the expectation through samples. And the idea there was to do tabular Q-learning. So the problem there is that you still have to keep a table of your states and actions, which still requires small and discrete state and action spaces, but at least you can do it for MVP to unknown transitions. And then we finally saw how we can extend tabular Q-learning to work with function approximations. But instead of keeping a table of all your states and actions, your Q values, you're just going to learn one set of parameters W that amortizes the prediction of your Q essays. And again, the training procedure is the same as Q-learning, which is that for this optimality equation, I'm going to treat one side as a target and treat one side as your current estimate, and try to minimize this difference using gradient descent. So that at optimality, you're estimating your Q stars where you're respecting this Bellman optimality equation. And we saw two main issues, one of which was you need to use an experience replay so that you don't have correlated samples. And you also need to use fixed Q targets so that you don't actually have this non-stationary prediction problem. And deep Q learning actually works for these high-dimensional states and actions, and also generalizes to these unseen states. Cool. So we have about 10 minutes left. Let me just give a brief introduction to some more applications, especially language and RL. I think this is what people are mostly excited about. But we're going to continue most of this next lecture. So a lot of these categorizations are from this very fantastic review paper at HCAI 2019. It's the survey of reinforcement learning with natural language, and that is one of the required readings for this week. And essentially, what they've done is that they've kind of classified all sets of possible tasks where we have language and reinforcement learning. So one of which are task-independent methods, and the other set are task-dependent methods. So in task-independent methods, the task actually doesn't require language. It's just that we are giving the model giving these agents some initial information that is pre-trained with language and vision. So for example, giving it word embeddings that tells it what these keys and skulls and ladders and ropes are. And the other set are more like task-dependent methods. So for task-dependent methods, that means that when you're actually in the environment, you have language provided. So language is given dependent on each task. And again, there's two categories here, one of which are language assisted and one of which are language conditional. So I think the easiest way to think about these is that for language assisted, you basically can solve the task without having language, right? If you look at these, you can kind of solve these environments. It's just that these language instructions that you're provided with, they assist you in solving the task, right? It gives you more information about keys and they give you more information about skulls. But if you don't have this information, you can still conceivably explore. It's obviously going to be much harder, but you can still explore and solve these tasks. Language conditional, on the other hand, basically means that you have, the task is only defined if you have language, right? Because in this case, you're given an explicit instruction, such as like, going down the ladder and walking right. So the task is not even defined if you don't have language. So these are more language conditional tasks. So we're going to look a bit at these both language conditional and language assisted. I think these are the main environments that have both your visual inputs and also some description. So for language conditional RL, there's three main classes, instruction following, getting rewards from instructions, and language and observation and action space. So for instruction following, you have these tasks, we have this environment, and you're just given these very simple instructions, which you have to train an agent to follow. So just go to the green torch. And the main difficulty here is that, during training and testing, you're actually given different sets of objects that you have to go to. Otherwise, the agent can kind of just memorize what each of these objects are. So the main research problem here is you have to do fusion. You have to kind of fuse your language and visual information. You have to align. You have to kind of look at each of these. You have to understand each of these descriptions and actually match them with what they're aligning with in the environment. So there's been a bunch of methods proposed for this. Essentially, again, you can set up these MDPs where an agent is interacting with an environment, is taking actions, and is seeing states where the state consists of both images and text. And you're going to get positive reward if you get it, or otherwise negative reward. So they've come up with many methods. I think this was a very popular method, which essentially does gated attention. So getting image representations and given text representations, getting a gated attention that learns a multimodal representation before you can apply basically any policy learning module. It can be deep Q learning, it can be like policy iteration, value iteration, any of these policy learning modules that we've seen in this lecture and that we'll also see in next Thursday's lecture. And they've actually shown that these methods are quite useful. So this gated attention method can actually effectively go to these different types of objects. Even when there's occlusion, right? Sometimes, so for easy, you have all of them presented to you. For medium, there's some clutter of objects. And for difficult ones, you actually only have partial observability. So you might have to might have to turn around and walk a bit more before you actually see these rewards. And they also found that different representations actually lead. They actually learn different representations for different attributes. So grounding, basically. So by seeing blue armor and by seeing red pillar, they can actually generalize to blue pillar. And why is that? And that's because they've learned separate representations for your color and your objects. And therefore, you can generalize to new objects of different colors. Cool. So other methods have also been proposed. I think this is a method that actually gives you more instructions so that you can get more rewards. So for example, you have, again, this Montezuma's revenge paper. It's a really difficult environment. If you just let the agent explore, it's not going to learn anything. But what you can do is you can get people from Amazon Mechanical Turk to play the game and describe certain entities that you should observe while succeeding. So you actually give instructions like jump over the skull while going to the left. And if you actually succeed in solving these intermediate goals, I mean, normally if you jump over and go to the left, you're not going to get any reward from the environment, but you can define these external rewards based on how well you can execute these intermediate instructions. And these can speed up learning. Yeah, so again, you can look more about in the paper, but essentially it encourages, it takes in these sequence of past actions and also these states that it's currently taking in, and it's also going to give it these external descriptions, and it's going to give rewards based on whether they've executed these external instructions successfully. And it shows that this speeds up training much better. And the last one, just one last thing before we finish. The other method is also based on instruction following, except that now you have much more long-term goals, and you're also doing this in a QA setting. So you're going to start with a particular robot agent in some environment, and you're going to ask a question. So what color is the car? So again, it's not going to see it immediately, but it has to do things like turn around. So I think this is a failure case. It wasn't able to actually reach there. It actually went outside the house to reach it. But yeah, so essentially it's partially observable. It has to maybe take some steps around the house before it can actually see the object in question, before it can actually provide the answer. Cool. So let's stop there. So today, we talked a bit about language conditional RL. Next week, we'll continue on how language can assist reinforcement learning for both domain knowledge and structuring policies. And we'll also talk about how we a different set of reinforcement learning methods based on policy gradients. Yep. So that's it. Here's a main summary for Deep Q learning.